Herkese merhaba. Emir şimdi bize topolojinin veri analitiği alanında nasıl kullanabileceğine dair yaptığı çalışmayı anlatacak. Emir söz sende, buyur.
Hello, everybody. Today, in this presentation, I will talk about topological data analysis in short TDA. Before start, let's look at the outline quickly. Firstly, I will give a motivation about topological data analysis to you, and then I will show the TDA pipeline. By following the steps in that pipeline, I will give an basic introductions about topological data analysis, and this pipeline is based on the example that I will show you for seeing the results. And let's start with the motivation. With the enhanced technology, there is a rising amount of data, and with traditional approaches, sometimes it is hard to analyze the data. So this results in noisy and high-dimensional examples of the data sets. So in that point, the topological data analysis might be convenient in some cases. Because it is a loosey process, you lose the excessive dimensions of the data, and it's a robust noise actually. Informally, in the first step, you have a data, and then you will give a shape to the data, and then by using homology groups and persistent homology, you get some topological indicators about the data, and by using statistics, you will have some ideas about the data. Formally, suppose that at first you have a data points S, which is embedded in d-dimensional space Y, and we assume that there is a k-dimensional unknown space X that sampled. The data is sampled from this X, and while sampling, the geometry and topology is lost. And in TDA, our aim is to recover this information. So let's start with the pipeline. Firstly, we'll have a time series, and by using Taken's embedding theorem, we will transform this time series into point cloud, and then by using simplicial complex and Vietto-Strips complex, we will give a shape to the data, and by using, like I said, homology groups and persistent homology, we will detect holes in the data, and then the information will be represented by persistent diagram. By looking at the distance between diagrams, we will have a comments about the data. So, how we transform time series to point cloud? We will use the Taken's embedding theorem, like I said, but since this theorem is about non-linear dynamical systems, and this is not our scope, the presentation, I will not give the proof of it. We will just use it, and you can read this theorem. And by looking at the theorem, we will pick the dimension D and the time delay, which is the phi function in there, and we will get a point cloud. So to clarify the idea, let's look the example of Lorentz attractor. Firstly, a time series given to us, xt, and by choosing the time delay minus tau and dimension S3, we will have a point cloud, shadow attractor, and if we picked this tau well, the original attractor and shadow attractor will be diffeomorphic to each other. And with the same process, we will convert time series into point cloud. So right now we have a point cloud, and now we are interested in giving a shape to the data by using point clouds. By the way, I didn't specify what point cloud is. Point clouds are just arbitrary dimensional discrete points that you can do linear algebra in it. And to clarify shaping, first let's talk about the polygons. As you can see there, by using triangles, we can get any polygons from the triangle, and by using dots and edges, we can get the triangle. And our main components will be dots, edges, and triangle. For 3D dimensions, that will be tetrahedron. So it is time to give a definition. Simplex. A K-simplex, denoted as like that, is the smallest convex set in a given Euclidean space Rd that contains K plus 1 vertices, which is represented as V sub I, such that I is an integer where each pair of vertices are linearly independent. And let's look at that. 0 simplex is dot, 1 simplex is line segment, and 2 simplex is triangles, and 3 simplex is tetrahedrons. And the K minus 1 simplex created by removal of vertex from K simplex is called face. And when we remove a vertex, we just represent as like this, just put a head on the vertex that will be removed. Then I will give a definition of abstract simplicial complex. K can be considered as a set of simplices where it is required that any face of sigma in K is also in K. And the geometric realization of K is the geometric realization of K is the embedding in some Rn, where it is also required that the intersection between any two simplices, sigma and another sigma, K, is either empty or a shared face, both them. And in general, we will consider geometric realization of abstract simplicial complex, shortly simplicial complex, and we will use them. So in that case, we should define a vector space. Why we use vector space is to define homology groups. Basically, we have to use the vector spaces of simplicial complexes, and it is denoted by C sub P K. And the field that will be used in general is Z2. There can be another field can be used, and the elements of this vector space is called P chains. Clarify this idea again. Let's look at the example. Suppose that you have a simplicial complex K. In that case, K has just vertices and line segments. By the way, this P is written for the degree. When P is equal to 0, we just construct a vector space just by using vertices, and when is 1, by using line segments. And in that case, since there is another, there is no another kind of simplex, the degree greater than P is equal to 0. So again, to define homology groups, we should define boundary maps to find the boundary of simplexes. P again stands for degree, and boundary P is defined from CPK to CP minus 1K, such that the summation of all possible face of a simplex. Clarify again this idea. Let's look at the example of this. When we put a one simplex as input, the boundary is like that. One should note that the consecutive boundary maps, composition of the consecutive boundary maps is 0. There is a proof about that, but since the time is limited, I cannot write, but I can show later to you. Now we are ready to define homology groups. We define homology groups to detect holes. And why do I mean by saying holes? Informally, hole is a topological object that an object is prevented by hole to continuously shrink. And to define homology groups, firstly we define p cycle and p boundaries, which is p cycle is subclass of p chains and p boundaries are subclass of p chains again. And p cycle is denoted by zp and is equal to kernel boundary p, and p boundaries are denoted as pp and is equal to image of boundary p plus 1. And homology groups is defined as the quotient group of zp and pp. So in order to get the number of holes, we will define Betti numbers, and Betti numbers, which is denoted by beta sub p, p is again for degree, is equal to dimension of the homology group. And when the degree is 0, the type of hole is connected component. When 1, the hole is loop, and when 2, the hole is a hole bounded by surface. So we discussed about the shaping in general and detecting holes, but we don't know how to construct this shape. In that case, we use Vietoris-Rips complex, and this complex was originally developed as a mean of calculating the homology at metric spaces. Construct that, we first define a parameter R, and for all subset of S. And if the diameter of the S is the less or equal than 2R, we include the simplex with vertices in S. And geometrically, it means that we define a R radius ball centered as the points in the subset S, and when the ball has non-zero intersection, we include the simplex. And to clarify this, let's look at the animation. As you can see, when the intersection starts, a shape is constructed. And when all vertices balls intersected to each other, all of them, the shape will be 3D. So in general, we do not interested in the exact value of R. We are focused on the increasing R values, and we will observe the lifespan of holes by looking at the change of the shape. And we do this with the powerful technique, which is called persistent homology. And for implement persistent homology, first we should define a nested sequence of simplicial complexes by using inclusion maps. And as you can see, it fits to the idea of increasing R. And the inclusion maps above sequence lead to index maps in homology. And we will use this map, F sub P over Ij. And this is defined from HPKI to HPKI Kj. And in persistent homology, there is a structure called classes. Classes are basically the holes, and when we say one-dimensional classes, we will think about the loops. And let's observe the classes, type of the classes, and to clarify this, I will draw a shape about that. Let's think as the time, the lifespan of balls, and when the class alpha, which is born at I, it cannot be in the image of the function, persistent homology function, since it cannot be mapped, since the alpha didn't exist in that case. And for the classes beta that persist from I to J, again, since it persists from I to J, it cannot be in the image of I minus 1 to I. And when the class gamma dies, these are the classes that in the kernel of f j plus 1 to j will be, this will be equal to 0. Or it can be mapped to another class. And there is no certainty that all classes will die. And the two notation will be used while representing the death and birth time, delta sub b and delta sub b. And in this example, you can see that there is no certainty that all classes will die. As you can see, data 0, 1 hole lived all the time, and one of them are born and one of them died. So we define we discussed about persistent homology, and now we have the lifespan of dots, holes, and we will represent to analyze the topological indicator. And there is many representation ways to do this. In this work, I will talk about the persistent diagram. Persistent diagram is basically two-dimensional graphic that one axis is birth and the other one is death. And the diagonal is here, and below the diagonal it is empty, since to die, firstly they should born, and that's it. So to clarify again how we represent this, we can look another animation which is based to the first animation. And as you can see here, this stays for the connected components, this stays for the loops, and this stays for the poles. So to analyze the topological indicator, we will look at the distance between the diagrams, and in order to do this, two metric is defined. One of them is P-Wasserstein metric. Here, phi is bijective, and one of them is bottleneck metric, which is get by taking the limit of this P to the infinity. And in real life, in general, the number of the points in persistent diagram won't be equal, and there is a problem since it is defined for phi is bijective. In order to overcome this problem, we use diagonals, and we can consider the diagonal that points born and die in the same time. And that's it. Let's look at the example application in time series and see the result. This data is obtained from stock marketing crashes, and firstly, the crash probability based on the first derivative is used. In the orange parts, the probable crashes is stated, and when we look at the TDA, we can see that the probable crashes are more specific and less noisy, and you can see the difference between results. Thanks for the listening.
Okay, I have a question. The first one is that I